We are in BEA5 again for the fifth instruction video. Today I'm going to explain to you what the possibilities are of the voltage controlled function generators, or V-FUGs. There are 16 of these in the studio, and they are built and designed by Sonology itself. And the name is maybe a bit strange for you, because when you look at modular synthesizers, you usually see something that is called a VCO, a voltage controlled oscillator. And then there are other devices called LFOs, which are low frequency oscillators, which are usually used for voltage control functions. Now, the function generators that we have here can do both. The name voltage controlled function generator comes from the time that Sonology pioneered in building and designing voltage control equipment. So the names that we are familiar with now, such as VCO and LFO, just didn't exist. And for nostalgic reasons, we stick to our own names. Now, these function generators are crucial in this studio. There's basically no patch that I will show in the upcoming instruction videos that will not use at least one of these, but probably several of them. This is why we have 16 also. The frequency of the signal that comes out of these function generators is set with the knob called tune. And the range of the tune knob is determined by a switch that you see here, which is the range. So if the range is 1 kilohertz, 1K, that means that the lowest frequency in this setting is about 0, and the highest setting will be approximately 1 kilohertz. Let's try that out. So here on the patch bay, the voltage controlled function generators are here. The first row of 10 and then another row of 6. They have two inputs, and I will explain those inputs in a minute. Then there are two outputs. One for the sine or triangle wave, and the other one for the block or pulse wave. For now I'm going to use the sine or triangle wave output, and I'm going to connect it to the mixing desk. So I'm going from this output to this input. We can see here on the LED bar that there is indeed a signal appearing at the input. If you're not familiar with the mixing desk, then please go back to the first instruction video. So I'm going to open the fader, send it to left and right, open left and right here. And there is the sine wave. So as I said, controlling the tune knob sets the frequency within the range that is determined by the switch. So if I go to 100, the highest frequency that I get here is 100 Hertz. If I go to 10 kilohertz, like that, the highest frequency is 10 kilohertz. And if I go to 10, then the frequency is between 0 and 10 Hertz, which is inaudible, but of course that is very useful when we use the device for control functions. Okay, so let's go back to the 1 kilohertz range. The signal is now a sine wave, but I can also take a triangle wave, which is richer in harmonics. A sine wave is basically a signal that only has a fundamental frequency and no harmonics at all. I'm going to make an additional connection on the patch bay, which is the output of the function generator to the input of the oscilloscope. We see the signal now on the scope, and we see that if there is no signal, there is a line here in the middle, and if I then connect the signal, this sine wave has a part where it goes above the zero line, and there is a part which goes below the zero line. This is because the function generator is now in the AC position. If I switch to DC, you see that the signal jumps up, and now the signal is between 0 and plus 5 volts, which is the usual range for voltage control in Sonology's voltage control studio. Now, when you use an audio signal, or when you use the function generator for audio signals, the usual setting is AC. When you use it for control voltages, the usual setting is DC. Although there might be reasons in some cases where a control voltage that goes between plus and minus is actually useful. But usually the control voltages are in the DC range and audio signals are in AC. So we switch now to triangle wave, and we see that the shape is indeed a triangle. If I go to the block output here, I get a signal that is even richer in harmonics, and we have now a square wave. A square wave that has a part where the signal is off and a part where the signal is on. And these parts are exactly of the same length. I can also change that length of the on period of the square wave, and I can do that by switching to pulse. And now with the duty cycle knob, I can control this wave length. So when I have a square wave, as I said, this part of the waveform is exactly of the same length as this part. That means that I have a duty cycle of 50%, half of the full length of the waveform. So when I switch to the pulse signal and I make something like this, I now have a duty cycle of 25%. A duty cycle of 25% sounds exactly the same as a duty cycle of 75%. And this is because the 25% duty cycle signal is identical to a phase inverted signal of 75%. This sounds similar to pulse width modulation, but it is not the same. And the reason is that the duty cycle is always proportional to the full waveform. Yeah? So if I increase the frequency, the duty cycle stays constant. So this becomes shorter and this becomes shorter. When I'm talking about pulse width, which we are going to do another time, I have a signal maybe like this, and I could say that this is 10 milliseconds. I can say this without knowing what comes here. Yeah? So even if I have one pulse, I can say something about the duty cycle. About the pulse width. But I can only talk about the duty cycle when I know the full length of the signal and the repetition. Yeah? So there is a theoretical difference, although sometimes it sounds the same. Duty cycle is proportional. The pulse width is an exact value. What should be mentioned as well is that when we are using the block or pulse signal output, AC and DC do not make a difference. Yeah? So the block and pulse outputs are always DC, they're always above 0. This is because we are not only using them as audio signals, but also very often as triggers, and then they need to be in that range. Now, apart from having control over these settings on the device manually, I can also use external signals to control the frequency and or the duty cycle. So this is what I'm going to do now. I'm going back to the sine wave. And it is now on internal still. But I'm now going to external control. So first the signal just drops because there is no input signal yet. But I'm now going to connect an external signal from the second function generator to the tune input. But first I'm going to set the right settings on the second function generator. So this is going to be on DC. I'm going to use a triangle wave, internal, very slow, so let's say around 5 Hz. And now I'm going to connect it. So I have a triangle wave. When the triangle wave is at the 0 volt level, the frequency of the first function generator is around 0. And when the triangle wave reaches 5 volts, the function generator number 1 reaches the maximum frequency of the range that I have set here. So if that range is 10 kilohertz, the voltage control signal can be related to the frequency of the function generator in 2 ways. One is linearly and the other one is exponentially. What does that mean? Linear means that there is a linear relationship between voltage and frequency. So if we would, for instance, have 1 volt equals 200 Hertz, we would then go up to 2 volts and we would get, for instance, 200 Hertz. If we then would go to 3 volts, we would get 300 Hertz. But this is actually not how we perceive frequencies. So it's rather inconvenient. An exponential relationship between the voltage and the frequency is much better. Why is that? Because if we are behind the piano, think about the explanations that I gave about filters. If we are at a certain key, let's say the C in the middle, we go 1 octave up, we arrive at the next C. That means that the frequency there has doubled. If we then go up another octave, which is perceptually the same interval, the frequency doubles again. So we need to double the frequency again and again and again to get the same distance in pitch. And this is what we get when we have exponential relationships between control voltages and frequencies. So listen to the difference. So we still reach that same high frequency, but the way in which we receive it is sounding as an equal speed of frequency increments. Whereas if it is linear, we feel that we drop to the low frequencies very fast and it slows down when we go to the high frequencies. This is exponential. So let's go back to the pulse output, so the signal with variable duty cycle. And I'm now going to modulate that duty cycle instead of having a fixed setting. So I'm back at the manual control of the frequency. But now instead of setting the pulse width by hand, I'm going to switch to an external signal. And the same triangle that was just now controlling the frequency is now controlling the duty cycle. So in the first patch I had a voltage controlled function generator, triangle wave, DC in the range between 0 and 10 Hz. Connected to the tune input of the function generator, which is on a sine wave, AC, between 0 and 1 kHz, exponential. In the second patch, I had the same triangle wave, and I was controlling the duty cycle, and then the duty cycle switch has to be on external. I use green here because green is a control voltage. One thing you might have noticed is that the output signal of the function generator is always at full level, meaning the full amplitude. And there are no knobs on the function generator to set the amplitude. So when I'm dealing with an audio signal, the way that I can control the amplitude is by manipulating the fader. Now the fader is a bit noisy, unfortunately. Now, apart from the fact that it is not so convenient to do this by hand, I'm not able to doing it very regularly, and also certainly not as fast as I might want to. So what can we do if we want to control the amplitude of this audio signal with a control voltage? We need an external device which is an amplitude modulator, which on a modular synthesizer is often called a VCA, a voltage controlled amplifier. So my function generator with the audio signal is now going into a VAMM, voltage controlled amplitude modulator, and then it comes out. And the signal that is controlling the amplitude is again coming from a second function generator, DC position, triangle wave, between 0 and 10 Hz somewhere. And that is then a green signal. So this is in and this is V. So the output of the function generator is now not going to the mixing desk directly, but it is going to an amplitude modulator first. And then the output from the amplitude modulator goes to the mixer. And the voltage input is connected to the output of the slow triangle wave from function generator number 2. Let's see how that sounds. Now this is the right moment also to demonstrate the difference between DC and AC as a control voltage. Because now it's obvious that when I reach the lowest level, I go up again to the maximum level. If I would be on AC, I do not reach the maximum amplitude because the peak of the voltage of the triangle wave is now 2.5 volts. Whereas the negative part of the triangle wave, so the part between 0 and 2.5 Hertz, just gives me a silence. Yeah. Which is nice if you want this, but this is the usual setting. If I use a square wave instead of a triangle wave, I get a signal that is just switched on and off. And this produces clicks, of course. If you listen carefully, you hear that the clicks are not sounding the same. Yeah, so they vary slightly. And this is because the moment where the signal is cut is independent of the phase of the sine wave. So it might happen at different points in the sine wave. The closer it is to the zero crossing of the sine wave, the smoother the click will be. If it is somewhere at the peak of the sine wave, the click will be very strong. So that was amplitude modulation of an audio signal with a control voltage. Now the control voltage itself, of course, also has an amplitude. And it would be nice if we could control that amplitude. And we can. We can even modulate it if we want. And we need a device called a DC multiplier. Now remember last time we discussed the AC multiplier or ring modulator. And I said that there is a device in the studio called a DC MUP. Sorry, I need to do that again. In the previous instruction video, I showed you the technique of AC multiplication or ring modulation. And we used a device for it called MUP AMM. And I showed that there was a switch on this device which had to be in the AC setting to do ring modulation. Now this device also has a DC setting, and then it does DC multiplication, which is what we are going to do now. So let's say that we have this square wave that looks like this. And this square wave is switching on and off an audio signal. But the peak is always the same. But now what I want is a next signal, a triangle wave like this. And this triangle wave is now supposed to do this. Yeah. So to gradually change the level of the square wave. And I can do that by multiplying those two signals. The formula for the DC multiplier is very simple. It is x multiplied by y divided by 5. Why is that? Imagine that the triangle wave is at its peak, so at 5 volts, and the square wave is at its peak too, then just by multiplying them, the result would be 25 volts, which is way out of the range of the studio standard. So when we divide the output by 5 volts, the multiplication of this 25 volts results in an output which is exactly the peak of the range between 0 and 5 volt that this studio is using. In other words, if the square wave is 5 volts and this one is at 1, the output of the square wave is at 1 volt on the output. If one of the two is 0, the output of the DC multiplier is 0. So let's try and do this. So here are the MUP AMMs. There are 8 of them. I'm going to use only the first one for now. So it has an AMM setting, in which case it is the same as the amplitude modulator that I was just showing. Then there is a DC setting, and there is the AC setting which we used last week for the ring modulation. So back to DC now. So I still have my block wave from function generator number 2. I'm going to connect it to the X input of the multiplier. I'm going to take a triangle wave from function generator number 3. Then from the output of the multiplier, I'm going to the voltage input of the amplitude modulator. The sine wave from function generator number 1 is the audio input for the amplitude modulator. And the output of the amplitude modulator goes into the mixer. So this is the function generator that produces the sound. This is the function generator that produces the square wave. And now here, this one has to be What I'm going to do now is to use a square wave to control the frequency of a function generator. And I'm going to put a device here which I'm not going to write down now. Because first I'm just going to let you hear what the result is. So this is now going to be on external AC, range between 0 and 1 kilohertz, connected to the mixing desk. So the sine wave is connected to the mixing desk directly again. I'm taking the block output of function generator number 2. I'm connecting it to the tune output input of function generator number 1, and I'm switching to external. So what I'm hearing is that at the top of the square wave, I hear the 1 kilohertz frequency, which is the maximum of the range. And at the bottom of the square wave, I hear nothing, because there is 0 hertz. Now let's say that I want to raise that lower frequency and reduce the high frequency, so create a small interval only. Now in order to do that, I need to introduce another device. And that device is a mixing amplifier. A mixing amplifier is a device that is designed to mix control voltages. So a mixing desk is made to mix audio signals. A mixing amplifier is made to mix control voltages. So I'm going to insert that device now. I take the square wave, I bring it to mixing amplifier number 1, and the output goes to function generator number 1. This is mixing amplifier number 1. I'm going to switch on the first channel and open the knob. So I'm controlling the amplitude of the square wave, and by that I am determining the highest frequency of the sound. So now I have a very small interval, but if I want to raise that whole signal, I need to add a constant voltage. And I can do that with the fourth channel, which is either a fourth channel on the mixing amplifier, or it is a shift voltage. And I can use it as a shift voltage by setting this switch to shift. So now I'm turning on this one. So if I turn this one off again, I'm setting the lowest frequency with the shift voltage, and I'm adding the square wave with a small amplitude. I'm going to add 2 more square waves from function generator number 3 and function generator number 4. And I'm going to add them to the output So I have the frequency of the 3 square waves, I have the amplitude of the 3 square waves, and I have the shift voltage. So that patch looks like this. In the first patch, I was showing how to use a triangle wave to control the frequency of a sine wave sound, whereby the triangle wave was slow, between 0 and 10 Hz, and the audio signal was between 0 and 1 kHz, and the relationship between the frequency of the audible signal and the triangle wave was exponential. In the second example, I showed the same triangle wave, but now used to modulate the duty cycle of a square wave. And then in the third example, we introduced a new device, a voltage-controlled amplitude modulator, so that the audio signal, a sine wave of around 500 Hz, was not having a constant amplitude, but the amplitude was modulated with a slow triangle wave. And that was also the moment where I explained the difference between DC and AC setting when you use a device for control voltages. In the fourth patch, I introduced the DC multiplier. And again, the DC multiplication is a function of a device called the MUP-AMM. So we have a square wave with a slow frequency, we have a triangle wave with a much slower frequency, and the triangle wave is controlling the amplitude of the square wave as a result of the multiplication of the 2 signals and then divided by 5. So the output of the DC multiplier here is controlling the amplitude of a sine wave of around 500 Hz. And then in the last example, I mixed 3 square waves, all 3 of them slow, but with unrelated frequencies. I've used the mixing amplifier to reduce the amplitude of the three square waves and mix them together. The fourth channel of the mixing amplifier was used as a shift voltage, so to transpose, so to speak, the sum of the three square waves, and the output of the mixing amplifier was then used to control the frequency of a sine wave generator. So that's it for today, and next week we will make another instruction video.